So we've talked about recursion. We want to know how this actually works. And Clarice and Andrew, you both are asking really good questions about like, how does the computer really work? How does it do this? Well, pretty much not just with recursion, but with the Python language, and not just with the Python language, but pretty much every programming language, and not just with the programming language, but with like the fundamental way, like sort of we were learning about like arrays and how stuff is stored in memory. Like at a really low level on a computer, there's the call stack. Like it's probably implemented in like the Linux kernel or something. It's probably even lower. In fact, it's probably at like the chip assembly code level. Because even like the device driver that handles like mouse clicks or the mouse or whatever has its own little tiny functions in like impossible to read assembly code or something. So at a really low level, a computer needs to be able to handle functions. And to talk about this a bit, I'm going to use a really simple example of two functions. And you can see there's these two functions here, greeter and greeter string. We're going to come back to factorial in a minute, but we're going to start with these. And you can see the one down here, greeter, literally it just calls this other function and passes it an argument name and then prints that. And this one just takes the name and returns hello, right? It's basically a hello world. And then if we run greeter with Ben, then we get a message. And just to type that out really quick, in fact, it would look something like this, you know, greeter string name. Sorry, return. Let's put this at the top of the file. And let me make sure I have this right. And I do. And let me go ahead and comment that out because we don't need that. And all these blue squigglies are just about Python wants me to add doc strings. And I've got my terminal over here. Should I move this back to the bottom? Do folks have a preference in terms of like clarity? Okay, cool. So that's pretty straightforward, right? And we're gonna walk through all this very explicitly in just a moment, but I figured it's always good to run a little code. Like when we run this program with the Python interpreter, the Python runtime, it reads through this file. It basically throws all these function definitions into memory in a lookup table or something. And then it gets here and it says, oh, all right, this is not like a variable or a function that I store in memory. This is something I have to execute. I'm supposed to call this function greeter and pass it a string. So let me pass that string. Let me look up this function, pass that in as the value name. Okay, now I'm supposed to execute this. I'm supposed to print. What am I supposed to print? Well, I don't know yet because it looks like I'm supposed to call this other function and pass it whatever that is, which I know is Alice because that's what I passed in before. So let's call this. I return. What do I return? I need to figure that out too. That's an F string. I need to do some string interpolation. Hello, Alice. Awesome. I know what to return. I return it back here because this is where that got called. Now I know what to print. I can print hello, Alice. The way that a computer keeps track of this is something called the call stack. We can talk about the flow of execution, an execution frame. The computer reads our code line by line, and the call stack is that stack data structure. And again, literally just think about a stack of plates. There's no secret magic to the stack data structure. That's its beauty. You can only take the plate on the top of the stack off. The only way to get to the plate at the bottom of the stack is by going through all the other plates. Um, and that's where it's going to kind of store these functions, is what we'll see. So the computer reads our code line by line. Greeter string is a function, so it's defined, but nothing is called. Greeter is another function. It's defined, it's saved in the lookup table or something, nothing is called. Hey, we've got a function. We're supposed to do stuff with it. And remember, this is how the Python runtime probably has its own call stack, but our computer also does it like a very low level. So this is like sort of a fundamental concept in terms of how computers and how programs work. So we've now added this function to the call stack, to the list of functions that we're supposed to call. In order to evaluate and figure out what that returns, we need to go inside another function, greeter string. So that gets added to the call stack on top of the other one. That one we can evaluate because we have this variable that's been passed into each one and it's being kept track of it. So that's something concrete, and that's returned. And note that here, like, we pass in, the argument of the name Ben, which then gets passed in over here again. And I think this actually is a typo. This should probably read hello Ben at this point. I apologize. That kind of slipped through our QA process, so to speak. Because this has pretty much evaluated and returned like hello Ben. So this should really read hello right there. I apologize about that. But the point is, we now have a concrete value for greeter to return. So kind of, please, to go back to your question, like what the return statement does, like it returns a value, and that's when like also a function gets removed from the call stack, right? And it's popped off the call stack, and its return value is returned to I guess it's technically called the call site. I don't really use that term, but Python is keeping track of where this code is called from, because there's namespaces and there's scope of all of that, and it needs to know what to do next in the program. And again, sort of that metaphor of sort of like magnetic tape or audio tape, and just like a little reader going like line by line down the tape, is sort of how to imagine what's happening here to some degree. So we can now finish evaluating this. We can print hello Ben, and it's popped off the call stack, and there is no return statement for this greeter function. So like where this code gets called, actually none is returned, but our program doesn't care, and it isn't doing about anything with that, and it's just like lost in the void, and that's totally fine. And if we did want to return a value with greeter, we could store it in a variable, which all of you have seen. Like if we wanted to do this, return success, right? We could just save that variable there if we wanted to. And now our program is really done executing, and the program stops. So that's sort of like a walkthrough of this idea of the call stack, and it's about like how programs keep track of stuff. And I think what I want to do actually is, there's this pretty amazing website that you all will play with later today. Called Python Tutor, and it lets us actually visualize this. We can do this too with the debugger in Python, and I want to do that in a moment as well. But for now, I want to put this in here. And actually, before I dive into this, I'm curious what questions people have or what's on people's minds.
Yeah, I have a question.
Go for it.
So I still don't quite understand when greeter is called. I don't understand how it knows to go up to the greeter string function. I mean, yes, greeter string is called within that print statement, but in order to call the greeter string function, doesn't the call have to be outside of that? Does that make sense?
I think the greeter string function is global, so it can be called from the greeter function.
Adam, you're muted.
Thank you so much. Sorry about that. Yeah, it's this sort of question like, hey, I call this greeter function, and then it calls this greeter string, but how does Python even know where this is?
Yeah, that's right.
Yeah. Yeah, essentially, like we're defining these in the global scope. There's something called a closure, which is where like the Python like it it will look to see what we need. Like that's why, like I'm pretty sure if I do x equals 7 def, just print x. Let's see if this works. It should work. Yeah. So this is the same concept, right? Of I define this variable in my global scope, but then I'm using it inside my function scope. I don't know exactly how Python does this. I don't know if it would be quite correct to say that like the function scope inherits the global scope. In JavaScript, what they do, and the term is a closure, which is basically when Python like reads this file definition, if it sees some variable that it doesn't have a definition for inside here, it looks a level up in the scope and finds it and then kind of saves it. So when this goes on the call stack, it actually includes like the stuff that it needs. So actually, like when this goes on the call stack, it includes this function definition. Short answer is like you can use stuff in the global scope inside your functions definitions and your function scope, if that makes sense.
Yeah, that makes sense. Thank you.
Awesome. Yeah, great question. Clarice, yes, what's up?
Okay, so I get the return statement, well, mostly the gist of it. Like it's kind of just putting that into a little box to use later. But for the recursive function, like with the factorial, we have two return statements. Like, how does it know how to address that, the ending return statement, I guess, when it's like, all right, return this, but it's already returning that other one. So like, what is it doing with that one, I guess?
Right. That's a really good question. And sort of like the magic of this, and this is what makes like recursive algorithms a little trickier to write. Like if I did like, n, just to come up with some random number, n equals 4, we wouldn't get very far here. Actually, I'll just print. Ignoring the hello Alice stuff. Like, now this is totally broken. So the program is only doing what it's told. So this, is not a very useful recursive algorithm because we don't get to this recursion. So the magic is actually in the way that like the base case is defined, because we're telling our program only go here when n is 1, and because we're doing a factorial, n is only going to equal 1 when we get to the end. So this never gets executed until the very last time, and this is the return statement that's get executed for all those other things, and then we hit this one when n is 1, if that makes sense. The magic is really in like our defining the rules for the base case and the recursive case, and we're going to walk through
I
this
guess
too. Yes, what's up?
I guess what is it doing with that when it's returning 1? Like we're getting the factorial version, but like what is it doing with the return 1?
Yeah,
Like is it multiplying that times our recursive 1, or is it just, I don't know, throwing it in the garbage? Or
it actually returns it and then multiplies it by all this other stuff. And in fact, I do, as soon as we get the other questions, I'm going to walk us through the call stack for this factorial function, and we're going to get to see that happen explicitly. Josh, yes, sir.
I think this answers Clarice's question. It's if n is 1, then it's just returning 1 factorial, which is 1, right?
So what our program does is if n equals 1, it returns 1. And you're correct that like 1 is 1 factorial. Our program has no idea about that though, just to be explicit. Like that's what we know and what we use to like write this algorithm. Let's walk through this. You know, I was gonna show this. I'll very briefly show what this is, but then we'll see it in the, we'll look at the recursive algorithm. So this is the cool thing about Python Tutor is, you know, we're talking about the stack and frames, and you can see stuff really explicitly. And part of your assignment today is actually to like walk through a recursive algorithm with this. But these are really good questions, and I do want to get to them. And so I think we should just dive right in. And I do apologize. Like I think this will help a bit, and then we can actually throw this in Python Tutor, and I really want to use the Python debugger a bit to show this too. So this is our same factorial method. Just the return statement is, the return statement is basically the same actually. This is our same factorial method right here. So let's walk through this, and these are really good questions about how is this base case handled, what happens to this one, and so let's see kind of what happens. So the computer reads our source code, it reads this function definition into memory, it sees that the name factorial occurs inside the function factorial that is being defined, and as we saw with that, like, you know, recursion stack trace exceeded, like the Python runtime and the computer has some knowledge of like what recursion is, so it doesn't end up in some sort of terrible infinite loop. It basically just is like, all right, this is recursive. So then we get to where we actually call and execute this function, and it puts this on the call stack, and then it runs it with factorial of 5, and n is 5. So we get here to this conditional, our base case, is n equal to 1? No, it's not. So this return statement is not executed at all, and we come over here. So this return statement isn't complete until we evaluate factorial of 4, 5 minus 1. So we got to add it to the call stack. So this return statement is not returned. It's not executed. And this is sort of the inception turtley bit. Think of like lots of nested parentheses, or, you know, you have like the way that you can like call a function inside a function, like we were doing with like print, you know, factorial of 5. And that's kind of the key thing to realize here, is that this return statement is waiting for this stuff that we've just put on the call stack. So this function call here, factorial with the argument of 5 has not returned anything yet. And we've just put factorial with an argument of 4 on the call stack. Same thing, factorial argument of 4, n is not, 4 is not 1, we don't do this, return 4 times factorial of 3. Well, we can't return for factorial of 4 yet, because we don't know what this is. I have to call this function again, and I got to put it on the call stack again. And we repeat this process again. So none of these function calls have actually returned anything yet. And this is sort of the weird and the cool part of recursion. Now with factorial 2, we're getting somewhere interesting, because factorial with 2 is the argument. Well, 2 is not equal to 1. We don't run this. We return 2 times factorial of 2 minus 1. Well, factorial of 1. Well, we still can't return for this function call. We still have to call factorial of 1. But now we get to our base case. And now this gets interesting, because n equals 1. We do return 1. This function call can return a value. We can pop that function call factorial of 1 off the stack frame, return 1 to the call site, to inside this other function call that's depending on it. So for factorial of 2, we've got 2 over here. Now that this one is returned, we've got 1. We've got 2 times 1. We can actually return 2. We can pop that off and do the same thing. This function can now return, this function call rather. So you see how the return statements sort of chain, and like when something's done, that value is sent back, and the call stack is sort of used to keep track of the order in which stuff happens and where it goes. And so this is kind of how this stuff gets wrapped up, because now we're getting somewhere, right? We've got 3 times 2 is 6, and we can return that to factorial 4. And now factorial 5, we can finally calculate, because we've got 5 times 24, which is all those other return statements returned and multiplied. So this is recursion. It is one of the more novel concepts in computer science, and it is also very cool. It's not used a ton in a lot of professional work, but it's like such a fundamental part of computing and how computers work that it's really valuable to understand it and feel comfortable with it, even though we're not going to use it on a day-to-day basis. So now is a very good time to ask questions, and Josh and Clarice in particular, I wanted to check in, but really with everyone, what questions people have about this, because this is sort of a new thing.
I have a question. So for some of the recursion solutions, like you could probably do a loop, or you could do recursion, or you could use map. But I noticed that with recursion, like it's actually gonna have like a much higher big O notation. So when's a good time to use it? Is it like something that's commonly done, or is it always preferable?
Yeah, that's a great question. As you pointed out, a lot of times you can implement something recursively or not recursively. To be honest, for most software engineering, especially like for web applications work, you all will probably not be writing recursive algorithms. I don't think I ever have for most of my professional work, because they are kind of tricky and they're usually not needed. They get useful for things like at a lower level, like if we have a tree data structure, like a lot of ways of like traversing or working through a tree lends itself to a recursive algorithm. As we sort of saw with factorial, like in some cases when we have something that's a little more math-like, if sort of the stars align, like a recursive approach makes sense. But it is not something like, we're not using recursion on a day-to-day basis. That said, like we're using things that use recursion, like Postgres somewhere in there, because Postgres uses a certain kind of tree for like indexing and searching, and it probably uses some recursion. But most importantly, really is avoiding recursion. Like the website Stack Overflow, that name comes from call stack overflow, which, as you saw from like when I kind of screwed up and had a recursive algorithm without a base case that went on forever, that can be a problem. So honestly, in terms of practical skills, half the value of understanding recursion is avoiding it.
That makes sense. Like made something recursive before and got stuck. Yeah.
Totally. And there's a great question too from Sean: is recursion common in interviews? I wouldn't say it's super common. At the same time, it is kind of like part of the expectation of like the common shared knowledge, I would say, for software engineering. Like this is such a fundamental part of how a computer works and how programs work. And it's one of the sort of like core pieces of a CS education. And even though we're not implementing recursive stuff all the time, it's still a tool in the toolbox, and also like making sure we don't do it by accident. So I would say, even though it's not on interviews, like a basic understanding is important. Because if you were like, well, I don't understand recursion at all, it I think would understandably cause some concern. And again, the analogy I would use here is like with a doctor. Like, do I expect my doctor to like, be a geneticist? No, but if my doctor was like DNA, that always confuses the heck out of me. I would find a different doctor. And Josh and Clarice, I see your hand up. I'm just kind of running through the chat. Is the call stack kind of like order of operations or a prioritized to-do list? It is exactly like an order of operations for the computer. It's definitely not a list since it is a stack, but this is the order in which our functions get executed, right? That's what the purpose of the call stack. And Clarice, yes, what's up?
Okay, so we talked about the return, the final return being multiplied. So if I was doing a recursive function with addition, like just trying to find the sum of each thing, would that change how the return statement acts, or is it going to also multiply? Like, wouldn't I return a 0 if I'm doing addition? I'm not sure if it just changes based on what it thinks you're doing or what.
The multiplication isn't actually coming from the return statement. It's coming from right here where we're telling our program to multiply these two values together. And then the return statement is returning that. And so like if I had changed this to a plus for addition, I don't know how well this is going to work, exactly like what we're going to get. But then this is adding these things together. So to kind of like walk through the call stack, like we recurse and recurse and recurse, n equals 1, we return 1. If instead of the multiplication symbol here, we just had a plus sign for addition, what would happen is right here, instead of 2 times 1, which was returned, it would just be 2 plus 1, which is 3, and it would just keep on going that way.
Okay, I think I get it. I get it now.
Totally. Yeah, recursion is definitely like, this is the reason that we kind of introduce it, and that there's a little bit of a warm up to it. Again, like you all won't be using this every day, and the goal here isn't like mastery, but like familiarity. That's really our goal with this, to be aware that recursion exists, that the call stack exists, and to have implemented once or twice a recursive algorithm, and like to know what a base case is. When should you use recursion? Andrew, that's a great question. Again, on a practical level, outside of the stuff we are working on this week, for pretty much everything in this class, the answer is never. Recursion can be a bit trickier. It is really like traversing a tree. It gets used for like lower level stuff that we probably will not be doing. Like simpler is almost always better, and so most of the time, honestly, we probably don't need to use recursion, and we don't want to. And this is what makes, I think, some of the stuff this week a little different. It's not directly applied, but again, it's not impossible that like a simple recursive problem would come up in an interview, specifically to test like their familiarity with recursion. And this is, again, I'd say it's like one of the like core pieces of sort of like knowledge of how programs work that I think is pretty much expected for professional programmers to understand. Like, you know, I'm rusty with this stuff. No one's expecting me to be able to knock off the more complex recursive algorithms left and right, like I studied in school. And if I was to interview for one of those West Coast tech companies that had maybe a lot of data structures and algorithms stuff where they wanted to see like fancier recursive solutions for certain things, or where recursion was used, I definitely would have to do some studying and brushing up on this. So this is really more of a general introduction, both to understand how computers better work and so that you have some familiarity just in case it does come up in an interview. But the key thing here is this with the call stack. This is like on a really fundamental level kind of how computers work, and I do think there's a lot of value to this knowledge because our field is always changing, you know. But a lot of these fundamentals are going to stay the same. Like arrays aren't going anywhere, the call stack isn't going anywhere, recursion isn't going anywhere, and all these other things get built up on top of that. And I do think there's something to be said, like the more that you learn sort of like the fundamentals that stay the same, I think the more it sets you up to have like a long and successful career and be able to learn new things. Also, you know, maybe not year one, but your second year certainly, and quite possibly your first year, as you're debugging, sometimes you dig into stuff like you have to look at the call stack, and it's just useful to know how this stuff works. And I mentioned this, and we saw this happen earlier, and the website Stack Overflow is actually named from this error of when the call stack size gets exceeded. Right? Because you can't just put stuff in there forever because we don't have an infinite amount of space. So that's another fun fact, and that's good to know. Again, like we're going to get a little more familiar with LeetCode later in the week. And this might come up in a technical interview, and that's a big part of the reason that data structures is talked about. I think there's a lot of value to it, but for better and worse, it is sort of, I think, like the shared core knowledge of the industry, and that's a lot of why we teach it. Sean, great question. Is a call stack based on RAM? RAM, random access memory, is just a place to put stuff, right? Like as is the hard drive. I'm pretty darn sure a running program would not put its call stack on the hard drive because it's something that you're accessing and interacting with all the time. So it probably would be stored in the RAM. I mean, CPUs have cache, which is like their own little memory for stuff that needs to happen really fast. So maybe there too. That's a little out of scope, but that is a good question. I don't have a good resource to recommend. I do recommend if you feel a little uncomfortable, like what's the difference between like RAM and like the hard drive. I'll see if I can find some good resources, but I do think it's worth doing just a little bit of background reading to get comfortable with sort of like those basic concepts of like sort of computer architecture and stuff. I never went that deep into them, But I do think a little bit of familiarity helps. So we have a bit of time. I would love, honestly, to walk through this recursive program in here, because I think this is quite cool. This actually lets us like see the call stack, like we can see the global frame and these functions that get called. We can see it gets called again here. And I think this can be a really useful way to visualize. I also wanted to demo running this with the debugger, because I think that's really valuable as well, which lets us walk through our code line by line and like see the call stack and all of these things. We're probably due for a short break. Before the break, I just want to see what other questions people have. Okay, cool. Let's do this. Let's take 10. And then I think what we'll do is we'll maybe walk through this factorial function again, probably in the debugger, maybe in excuse me, the Python tutorial program. And then we can take a little time, and there's a couple of recursive tutorials, or maybe even look at one of the assignments from today and work through a little bit of that as a group to implement some of this stuff. So why don't we take 10 minutes and then we'll just I'll definitely show you guys the debugger, because that's a good thing to see, I think, and really helps make this concrete. So we'll do a little bit more recursion in 10. Cool. Thank you, everyone. See you in a bit.